Hi everyone, welcome back. So we're gonna keep going through this chi-square goodness of fit example. So remember, we're working with the Pokemon data. We've done our prepare steps, so we've written out the hypotheses, we've looked at the sample data, seen that in the sample data there's a preference for Squirtle, but is that enough evidence to conclude that there's a preference in our entire population? That's what we're working toward. And so just like when we in our previous hypothesis test, there's also going to be a check step. And so this is the first time where we're actually going to talk about what this independence condition means. And so independence refers to independence of observations. And so what we want to ask ourselves when we're determining if observations are independent, it's easiest to always discuss this with an example. And so in our Pokemon example, um, does knowing, we'll say, does knowing your neighbor or friend's preference influence your own when answering this question, or when answering the Pokemon question? So in this case, it was an online quiz that you answered this. And so the answer to this question is probably no. So if you answer no to this question, then that means that you are assuming that the observations are independent. Because each observation is giving you a completely new or independent piece of information. If the answer to this question was yes, maybe you're sitting in a group of friends and then you discuss which Pokemon are your favorite and then you all answer the same Pokemon, then the observations aren't independent because each new observation isn't giving you completely new information because you all kind of talked about the question first. Okay, so if that doesn't click quite yet, we'll see a couple more examples of this. This is just the first time we're kind of introducing this notion of independent observations. We also have a sample size condition, just like we had before. So before, our sample size condition was that n times p0 is bigger than 10 and n times 1 minus p0 is bigger than 10. Now our sample size condition is going to be that all expected counts are larger than 5. I'm going to put some dots there because we haven't actually talked about what expected counts are. And so we'll come back to this in a sec after we do the first step of this calculate part where we figure out what our expected counts will be. The way we want to think about expected counts is we want to think, okay, if our null hypothesis was true, what would we expect our counts to be? So that's where the name comes from. So if the proportions were all actually equal to a third, and we had the sample of 56 students, what would we expect the count of people who prefer Bulbasaur to be? What would we expect the count of people who prefer Charmander to be? What would we expect the count of people who prefer Squirtle to be? And so we could just figure this out as Bulbasaur. So if the true proportion was a third, then we would expect out of 56 people, we would expect 18.67 of them to prefer Bulbasaur. And it's fine that our expected count is a decimal. That'll just go through in the calculations. For Charmander, again, if this null hypothesis was true, how many people would we expect to prefer Charmander? Well, that's going to be the same exact calculation because Charmander is, again, a third in the null hypothesis. Squirtle is, as you could probably guess, the same deal. All right, so if our null hypothesis was true, we'd expect about 18 or 19 or so students to prefer each of these Pokemon types. Back to our condition then, we could say that this holds here since each expected count is 18.67, which is larger than 5. Okay, so this would be like what we would expect our data to kind of look like if the null hypothesis were true, kind of give or take some. If our alternative hypothesis were true, then we would expect the observed counts, so what we actually saw in our data, would look really different than the expected counts under the null hypothesis. All right, so that should make some intuitive sense. If our alternative was true and there really was a preference, in some way we'd expect our observed counts to be super different than what we calculated as if the null hypothesis were actually true. Now we want to kind of take that intuition and put it into a more formal statistical test. Previously, we had this z-stat where we had our point estimate minus the null value divided by the standard error. That was our test statistic, and that's how we figured out what the p-value was for our one proportion hypothesis tests. Now we're going to have a slightly different test statistic, and it's going to follow a different distribution than the normal distribution. And so this is the part that will be most different between the chi-square goodness of fit test and our previous kind of one proportion hypothesis test that we spent so much time on.